So I may give like a bonus assignment or something. You guys will interpret that as me trying to help you through grade. I will interpret that as me trying to help you understand organic chemistry. We won't maybe see eye to eye on that. Anyway, like more important than the score, well, there's some of the score, right? If you look at how the grade is distributed in the class, like each exam's 100 points out of 500, like it's pretty solid back to your grade. So, you know, made a 12, you should get out, because mathematically it just doesn't work out. You know, ace everything else. Having said that, people tend to, especially in organic too, people tend to make what they make, right? Like you've seen organic 1. You should read carefully what I say in that long announcement about organic 1. There's sort of 2 reasons you might bomb exam 1 in Orgo 2. It might be that you're not picking up new material. That could be a bunch of reasons. Maybe you got sick, maybe you partied, maybe you found a romantic interest that was more interesting. A lot of reasons, right? That you might not do well on 1 exam. Another reason is you don't have a good foundation in Orgo 1. That sometimes happens. Sometimes people pass Orgo 1 and don't actually have that solid foundation, and that's a dicier situation. I've said many times, and I'll say again, if you have a repeatable grade in Orgo 1, like unless you ace this exam, you should get out and take Orgo 1 again. Orgo 1 leads to Orgo 2. If you're not solid on Orgo 1 and can retake it, do that before you finish this class. Like I said, if you made a D- in Orgo 1 and you happen to ace exam 1, I'd probably stick around, because then you've got 100 points toward the end. Anyway, you know, those of you at the really high end, congratulations, you haven't cinched anything, right? There's a lot of 3-0 football teams in the country right now. If you totally bombed it, you know, we at least need to talk, or you need to give some serious thought. I'll also remind you there is a W deadline, a withdraw. Students tend not to like that. I find nobody cares. If you have a W on your transcript, nobody's going to look at that and think anything about it, all right? Unlike maybe an F. So on the other hand, I don't think exam 2 is before that deadline, but you know, there'll be some quizzes in class and you can kind of check that out. So if you're sort of, I don't know if I should drop or not, I don't know how well I understand it, maybe hang around, see how it's going. If you get, you know, if we come up to the W deadline and you're still drawing 5 bonds to carbon, or think that QR is a atomic symbol, then you know, then you can drop. Okay, so put exam 1 out of your mind right now, except for all the chemistry on it. Like, remember the chemistry, don't worry about the scores. Where we're going next, we're going backwards. So where many of your friends started this semester in chapter 12. Chemistry of alcohols. These 4 chapters in my mind, 12, 13, 19, and 20, all sort of fit together pretty well. We're going to spend quite a bit of time in 12, not a whole lot in 13, and then 19, 20, and 21 we'll spend a lot of time on. And I don't know where I put 20 up. You know, at this point we're pretty much going in order. Exam 2 will be in here somewhere. I don't know exactly where. On one hand, that's a lot of material. Like you might think 5 chapters of material. On the other hand, it's all pretty much related. So I hope you'll see. Any questions? I'll save last stuff for lab. If you're in my lab, I'll go ahead and apologize for. And if you're not in my lab, you might have gotten a message from me last night. I posted an announcement to the wrong. I'm part of Dr. King's Canvas lab, so I can see she's coordinating, so we can all see what the. Anyway, I sent that group an announcement. Okay, so alcohol, please. So there's your sort of generic alcohol, right? Not any OH. Carboxylic acid. So just because you see an OH doesn't mean it's an alcohol. but it's still an OH group, and they kind of do the same. OH groups tend to do the same chemistry. I mean, I haven't said this specifically in this class, but we call these things functional groups, and we sort of do chemistry by functional group for a reason. Any compound with an OH in it is going to kind of behave similar. This carbonyl changes the behavior of that OH enough that we actually call it a different functional group. Right, that carbonyl is electron withdrawing, so it's pulling electrons away from the OH. That makes that H way more acidic. You guys should know that at this point, but the thinking about carbonyl as an electron withdrawing group maybe helps cement that. So, and in between this, we've already talked about these a little bit. This phenol. Again, that's an ROH group. And it sort of maybe behaves a little more like an alcohol than a carboxylic acid, but it's different enough we need to consider them separately. So let's just put up everybody's favorite alcohol. There's ethanol, and we'll put up a specific acetic acid. And if you're these three molecules, you should, maybe 20 years from now, you won't remember the structures of them, but these are three compounds you're going to encounter in the world. If you happen to be anywhere remotely close to a chemical business, I would include medicine, biology, a lot of engineering, any of those, you're going to encounter these. All right, phenol is a common disinfectant, and phenol is a really common component of a lot of natural products. Ethanol is everywhere. It's not just booze, right? It is a really good solvent. It's made from petroleum. You can make it from petroleum feedstocks as an industrial substance. We tend to make it from foodstuffs if we're going to drink it. If you want to make this 100%, so again, you may know this. If you want to make 100% ethanol, which sounds really cool, you have to drive away water. Ethanol azeotropes with water. So the purest you can make ethanol by distillation is 95%. That's commonly sold at liquor stores everywhere. To get that last 5% of the water out, well, you really don't need that to get drunk. Okay. But to do that, you have to distill with other things that azeotrope with water. The common one is benzene. Benzene is carcinogenic. So if you find 100% ethanol, there's always a trace amount of benzene in it. Makes it a carcinogen, makes it not suitable for consumption. So really, don't do that. And it lets us, if you ever see us in the stock room, have a giant jug of 100% ethanol, that is way cheaper. That giant plastic jug, 5 gallons of industrial ethanol is probably cheaper than a fifth of vodka. And the reason is we don't pay tax on it, right? The government taxes ethanol the way they tax cigarettes. They want you not to consume ethanol in cigarettes. They know you're going to, and they want money, so they tax it. 100% ethanol, you can't. That's not going to be on the exam. It's just a fun story chemically educated people should know. Where are we going to find acetic acid? Vinegar. It's in vinegar. So you also get this from fermentation, and it's important to note that the way you get acetic acid is oxidation of ethanol, right? So you can make vinegar by fermentation just the same way you can make ethanol by fermentation. And you guys do this, in fact. I don't mean you guys, perhaps you don't drink. Any mammal that consumes ethanol has an enzyme called alcohol dehydrogenase, which oxidizes the ethanol up to acetic acid. You can actually live on ethanol, not very long. It's not a good nutrient, but you can oxidize it and get some energy. The intermediate step for that, these are different colors as the red is bad. Halfway through there, that's lovely. Tell you what, I'll stop trying to use this as well. All right, the intermediate to that is an aldehyde. We're going to see this. Chemistry of aldehydes is in chapter 19. Chemistry of carboxylic acid and carboxylic acid derivatives is in chapter 20. So right there, you see how they're connected. Anyway, we oxidize ethanol up to acetaldehyde and then again to acetic acid. This is how a breathalyzer works. So breathalyzers don't detect ethanol and don't detect acetic acid. They detect acetaldehyde. Right, it's a volatile component. There are some people who are born without alcohol dehydrogenase. One, they really shouldn't drink. If you have friends like who have this, I wouldn't call it a problem. It actually like doesn't affect you at all unless you drink alcohol. But if you have that, you can drink a ton of ethanol and you'll never register on a breathalyzer. You'll be drunk as hell, like really fast, all right? Like you can't metabolize ethanol. So if I do a shot, like if a person with normal alcohol dehydrogenase does a shot, immediately your body's like, oh crap, like we got to do something with this. And you start metabolizing it. And so if you question.
Yeah, I was gonna say that's also why you can't drink methanol because it produces formaldehyde.
Right, exactly, yeah. And I'll mention that. Where's my flag? All right, so if you ever have a friend who does not have alcohol dehydrogenase like I once did, do not have them be the designated driver just because they'll blow zero, right? There are other ways for people to tell that you're drunk. And they will tell, like they turn bright red, they can't stand up straight, focus their eyes, all that fun stuff. But this is an oxidation, okay? So if we take ethanol and we oxidize it to acetic acid, what are we doing? We're adding more oxygen. So in chapter 12, we're going to talk about oxidation quite a bit. The reverse process, I'm skipping over phenol here and I'll explain why in a minute. Right, the reverse process would be to take an aldehyde or a carboxylic acid or a carboxylic acid derivative and take it down to the ethanol. We're adding hydrogens at that point, right? In organic chemistry, if we add hydrogen atoms, that's a reduction. From Gen Chem, you probably remember that a reduction is an addition of electrons, an oxidation is a removal of electrons. And it actually does work that way, and we'll see how that works in a minute. All right, I haven't mentioned phenol in all this, and so we're going to omit section 12 of chapter 12. That's oxidation of phenols. Not because it's not important, I think it doesn't fit with the rest of the material quite that well. So I will just kind of mention here, this is a pretty common thing to do. You can oxidize a phenol. You're right, that carbon has 4 bonds already, there's no hydrogen on it, so we can't lose the hydrogen. So what we have to do is we basically have to oxidize the entire ring. That's a pretty dramatic oxidation. And that will actually happen just sitting around in air. Phenols, especially phenols with electron donors on them. Remember, for something to get oxidized, I've got to pull electrons out of it. So if I've got an electron donor on there, got more electrons to give away, easier to oxidize. And this happens in nature. There are a lot of biological cofactors. You'll see these in biochemistry, biology. So going to the right, this is a reduction. Going to the left, this is an oxidation. And it's reversible. Like I said, we're going to omit chapter 12. I've basically just shown you chapter 12. That's what they do in chapter 12. I'm going to trust if that's important to you, you're going to take biochemistry someday, and you're going to see quinone cofactors and quinone-like cofactors. Photosynthesis does this a lot. This is basically an electron shell, right? There are a lot of enzymatic cofactors that can sort of store electrons as a hydroquinone and give them away and become a quinone and just go back. Cool reaction. It's cool chemistry. I'm going to omit that so I don't spend 3 weeks on it. Okay. Is that on there? It's not even on. Sorry, guys. The glare today. Okay, so now that I've sort of introduced all this, let's think about, let me draw some. All right, so I've drawn ethanol. Properly, this is ethyl alcohol. And note that I don't have to do any numbers. I don't have to put any positions. There's two carbons. Two carbons have to be bonded to each other. And if there's no H on one carbon, then there's a CH3 on the other. Like ethyl alcohol by itself doesn't need any help in it. And again, we usually shorten this to ethanol. Out in the world, you just call this alcohol, right? Somebody on the quad says alcohol, you don't have to think, do they mean? Right? Do they mean that that's alcohol as well? But probably your history major friend on the quad does not mean that. They say alcohol. So what is the name of this compound? It's a hexanol. What's 3? So there's a couple of different ways to write this. You can write it 3-hexanol. You can write it hex and 3-all. This is actually the way the bureaucrats at the International Union of Pure and Applied Chemistry like it. It's a terrible way to name things, right? Like you can't say a number in the middle of a word. We don't typically do that. So like you don't insert numbers, you insert like the F word. That would be how you do that. Here, this is a much better way to speak it. So if you hear people speak, they're going to say this. If you write it down, that's it. On an exam, if I ask you to name a compound, like either one of those would be fine. This is a chiral center, so you're going to get an R or an S in there somewhere. If it's racemic, you don't have to really say any of that. 3-hexanol is understood to be racemic. Things are understood to be racemic unless somebody specifies like 3-R-hexanol. Okay, so chemistry of when I say chemistry of an alcohol, what do you guys think about first? Anything. Basic. And yeah, so there's acid-base chemistry, there's nucleophilicity, right? So the OH, right? The OH the oxygen has lone pairs. So like water, I guess that was the other thing. Another molecule with water is not an alcohol. I say that, you should play that on your friends. So they ask for alcohol, get water, there's no H group. Clearly, it's not the same compound. But the chemistry of water really does, in a lot of ways, look like the chemistry of an alcohol. So if I take, if I say water is going to be a nucleophile, I can have an alcohol be a nucleophile. They're all weak nucleophiles, so alcohols are weak bases. Therefore, weak nucleophiles, weak acids. What else? There's some kind of related to acid-base chemistry that is important. What's that? Protonation, deprotonation. I was thinking hydrogen bonds. So like ethanol, solubility of ethanol in water. Well, first of all, let me ask you a question. Is ethanol soluble in water? Right. Don't search your mind for organic chemistry knowledge there or gen chem knowledge, right? You've all seen wine, beer, spirits, one phase. Ethanol, in fact, is completely miscible with water. Right? I can mix any proportion of water and any proportion of ethanol, and it'll stay one phase. That is not true for many compounds. And the reason it's true, let's say we've got water here, right?
They want to take.
So all of these can hydrogen bond to each other. Right? Yeah, oxygen's got electrons. Oh, there we go. You could have the fifth one. And I know I talked about this some at the beginning of the year. Right, water is constantly hydrogen bound to each other. If you think about physical properties of molecules, we teach in Orgo 1 that molecules have a higher boiling point and melting point. The heavier they are, the bigger they are. That molecules sort of have this, they have what's called van der Waals forces, dispersion forces. Molecules are a little bit sticky. So in one sense, they really do repel each other. If I take two molecules and I just try to squeeze them together, they will repel each other. But they also have just a little bit of a non-covalent interaction. So then you've got dipole-dipole is a stronger non-covalent interaction. Hydrogen bonding is even stronger. And finally, you have ionic interactions like a cation and an anion. Okay, so water, the water you're drinking is constantly hydrogen bound, but they're non-covalent. So if I could put a GoPro on an oxygen, it would make a hydrogen bond and break a hydrogen bond a few 100 million times a second, right? Those bonds form, they break, they form, they break. But they're still stickier than you would think otherwise. Pretty much every other molecule we know that has a molecular weight around 20 has, oils at minus 200 or something, because they really want to be a gas. Water, on the other hand, oils at 100. It's our definition. You guys mostly encounter water as a solid. What the hell am I saying? You mostly encounter it as a liquid. You're either not paying attention or you see a lot more ice than I think you do. Okay. So again, not to go into too much thermodynamics, but for something to dissolve in something else, it has to interact with it, and it has to then replace the interactions that molecule has, right? So if we come in here and say we're going to break it, we're going to replace one of these waters, right? That means we break two hydrogen bonds. Those hydrogen bonds are positive interactions. So if I take something like, hexane, hexane can't hydrogen bond. Doesn't have any dipole to speak of. And so really what we've done is we've just replaced two positive interactions with no interaction. That's energetically unfavorable, so it doesn't happen. So hexane is not soluble in water. But if I replace it with ethanol, right, the two positive interactions remain. I do get a little bit, right? That bit is not favorable. But it works out that the ethyl's small enough that it doesn't cause any problems. So ethanol remains as again, it's completely miscible in water. How about this molecule here? Is 3-hexanol going to be more or less soluble than ethanol in water? Be less. Do you think 3-hexanol is soluble in ethanol? Yeah, it is. Because now you've got the OH hydrogen bonding, you've also got the ethyl can interact with you've got two non-polar components. So really, the more similar two molecules are, and the more they have the same sort of non-covalent interactions, intermolecular interactions, the more likely they are to be soluble, and the more soluble they'll be. So I give you some numbers. Again, I'm not asking you guys to memorize these numbers. So the way to phrase this is infinitely soluble. And the molecule I picked, I didn't end up drawing the same molecule, 3-methylpentanol. Sorry, don't throw that. So 3-methylpentanol, which is, it's a hexanol, it's going to be about the same. You can actually dissolve about 0.5 gram in 100 grams of water. All right, so it's not like insoluble, but it's pretty close. I don't know if anybody's going to watch this, but just in case. And then we've got phenol, like I said. So we talked about acid-base chemistry. pKa of ethanol is about 16. pKa of these others, 16. Really, what I would like you guys to know, the range of pKa for an alcohol is 16 to 18. Remember, the higher the number, the less acidic it is. Okay, so alcohols aren't all that acidic. We said they're weak acids, weak bases. Ethanol in general, you can't drink strong acids. So if I said here, have a shot of sulfuric acid, you should say no. I would hope anyone in this class would say no. I would hope anyone would say no. If it's your 9th shot, maybe you say yes. So don't offer it to anybody if they're inebriated. All right.
You said the more something, the more acidic.
Higher the pKa, the less acidic it is. pKa is an inverse relation.
Yeah. So we're talking about like the alcohol, more zigzag.
Really, it doesn't. Yeah, these things don't have that much of an effect. Like this alcohol, primary versus secondary has some effect, but the pKa of ethanol, I actually don't know exactly what it is. Yeah, here's the other thing about pKa. You're going to hear me say a lot in this class. pKa of this molecule is whatever. If that number is outside 0 to 14, it's mostly interpolated. All right. pKa is defined as being in water. pKa of H3O plus is 0. pKa of water is 15.7. So pKa is outside that range. Like you can't actually have it. The strongest acid you can have. I'm gonna write that down. This is an important thing. This is not important for this chapter necessarily. It's just in general. We call this the leveling effect. You guys should have heard this before, but it's not. All of us have a bad habit of hearing things. We know we're going to be tested on it. We get tested on it. We purge it. Right? That's not important information. Again, if you're going to be working with chemical systems, especially chemical systems in water, so again, I would include like human beings in that. This is an important thing to remember. All right, the leveling effect says the strongest acid you can have in water is H3O plus. If I put an acid in water that is a stronger acid than H3O plus, that acid will protonate water molecules and I'll get H3O plus. The flip side of that is, and this is actually going to be a lot more important in this section of the class. The strongest base you can have in water is hydroxide. All right, so if I put a base into water that is a stronger base than hydroxide, that base will pull a proton off water and make hydroxide. We're going to see that a fair amount, quite a bit, not so much today necessarily, but as we get down to 19, 20, and 21, we're going to be using bases and nucleophiles that are way stronger than water. And you want to make sure there's no water around. Yes.
What would be the solubility of 3-hexanol?
It'd be about the same as this, 6 carbons OH. Like it wouldn't be exactly the same because the shape of this does have some effect, but it would be pretty close.
Does that mean that water's like the weakest base? At like conjugate base?
No, it didn't mean that at all. It just means that the other way to phrase this, you're going to think about a more general thing than this. We make it a general thing for water because we deal with water so much. So at the minute, we're mostly water, so we think about chemistry and water. But basically what it means is You can never have a stronger acid in a solvent than the protonated form of the solvent. You can't have a stronger base in a solvent than the deprotonated form of the solvent. Right? It's just water is so commonly the solvent. So when you guys did, crap, I can't even remember what lab that was. Like 2 weeks ago, you did a Grignard reaction. You made a dye of some sort. You had to exclude water. Remember we gave you glassware that had been in the oven? The reason for that is that Grignard reagent is a super strong base. We're going to talk about it, probably not today, but next time. And if I put a Grignard reagent in water, water just protonates the Grignard reagent. I get an alkanes or a benzene and hydroxide. That doesn't necessarily it doesn't have to be in water. So the other thing that is hard to think about, maybe I'll make my lab do this sometime. It's just, again, water is this tiny molecule, weighs 18. So a millimole of water is like 18 milligrams. Right? The density of water is 1 gram per mil. So that's 18 micrograms of water is 1 millimole. So if I have 1 millimolar reagent of Grignard, I only need 18 microliters of water to totally quench it. Right? So you don't have to be in water. If you just have a little bit of water in your solvent or on the glassware, it screws up the reaction. Okay? Question? Okay. So again, this is a good thing to keep in mind. That's the solubility rules. You had a question about so this is not this, I didn't draw the same molecule, but 3-hexanol and 3-methylpentanol are pretty similar. You've got 6 carbons bonded to an OH. They won't have exactly the same, but it's not like this one change is going to be enough to make it more like ethanol. Generally, the more carbons you put on there, the more insoluble it will be in water, the more soluble it will be in something like hexane. Phenol then is in the, I guess I should, I'm really hopping around this sucker. pKa of carboxylic acids. This is going to be like 3 to 5, right? The carbonyl makes that carboxylic acid a lot more acidic, makes that OH a lot more acidic. Remember, pK units are orders of magnitude. So if something has a pK of 5, it's 10 orders of magnitude more acidic than something that has a pK of 15. So it looks like not a big number, but it's an enormous number. So that acetic acid, the pKa here is 4.5. So that's 11.5 orders of magnitude more acidic than ethanol. That's like roughly 1 trillion. That's a lot. So ethanol, if I drink ethanol, the pH of my mouth is somewhere around 5 or 6. I think it's huge. So at pH 6, it's a long way from 16. All the ethanol is protein. It's just neutral ethanol. That's what I drink. Carboxylic acid, if you eat a carboxylic acid or drink a carboxylic acid, it's going to be mostly deprotonated. If it goes into your mouth protonated, it's going to protonate your mouth. Right? So drinking vinegar is very different than drinking ethanol. All the way around. So ethanol will burn. One day when you're older, you'll experience this maybe. Ethanol straight like Everclear. If you ever are stupid enough to do a shot of Everclear, I see some defiant looks. All right, like it burns. It's not burning because it's acidic. It's burning because it's sucking water out of the tissues. Right? It's drying the tissues out. It's hygroscopic. So it's a completely different burn than drinking strong acid. Has anybody done a shot of vinegar? Like vinegar is completely safe to drink. It's not pleasant to drink, but it's safe. Yeah, you should try this. So, like don't drink like HCl or sulfuric acid, but vinegar is, and they make some really nice balsamics that taste really good. Like, but they sting a little bit. Spicy, like there's stuff that can go in your mouth and sting you without like being dangerous. So avoid super strong acids. Acetic acid is fine. Acetic acid, carboxylic acids are like the strongest acids for biology. Amines are the strongest bases for biology. So you can eat amines, you can eat carboxylic acid, it's fine. Okay, hydrogen bonding. Yeah, the whole point here was hydrogen bonding is very important. How's that? 30 minutes to make this important statement. And hydrogen bonding really dominates the chemistry of or the physical properties of alcohols. So again, just to sort of highlight that, remember that molecules the same size tend to have, all else being equal, molecules the same size will have the same boiling points or similar boiling points. But that OH really throws things. So ethanol here boils at about 78 degrees C. Propane, which has a molecular weight almost the same, physical size very close. Anybody want to hazard a guess for propane? Well, first of all, room temperature, is propane a gas, liquid, or solid? It's a gas. What's that? You got to vote for negative 100. Price is Right rules. Higher or lower? Oh, the Price is Right the whole time. It's still on, right? Oh. What's that? Oh, that was you say higher or lower? It is higher. Minus 50, higher or lower? All right, fine. Minus 42. You can pressurize it. You guys can go to the store today and buy a little cylinder of propane. You probably carried it if you've gone backpacking or something. But those two molecules are basically the same size. If a molecule that size only has van der Waals forces, those molecules at minus 40 degrees, they are going to be gas. Ethanol actually at minus 40, I think, is a solid. I forget the melting point. I should have looked that up. Anyway, it's not important. Okay. That's the drinking side of my family. But your cousins look at you funny when you give this lecture on the beach in the middle of their parents' funeral. I didn't know. Okay, so let's think about how you might make an alcohol. You guys have seen some reactions. Oh, you know what? I totally blew past this. Phenol has a pKa of 9.9. You can consider that 10. Phenol is in between a carboxylic acid and an alcohol in a lot of ways. The pKa comes in between because if you put an O- there, it delocalizes around the ring, right? So phenols are fairly acidic. They're not acidic. Again, if you eat phenol, don't do that. But if you eat phenol, it's protonated when you eat it. But if you no, you really can't. If you add hydroxide to phenol, that proton comes off. Right. So OH minus is less stable than phenoxide, O minus. All right. So preparation of alcohols. So I can make an alcohol, a primary alcohol, by doing SN2 with hydroxide. Hydroxide is a good nucleophile. If I have a molecule that will do a good SN2, then I will get an alcohol out of that. Right? So SN2 is the concerted one. OH makes a bond to the carbon, kicks out the chlorine, chloride. Well, the same is true. The mechanism is a little more complicated, but you can make alcohol by doing SN1 with water. I'm not going to draw the mechanism right now, but if you use water as a nucleophile and SN1 reaction, you'll get an alcohol. That's chapter 7. You can hydrate an alkene, right? This looks a lot like what we just got through talking about. If I take an alkene and I treat that with acidic water, I get an alcohol. So again, the SN1 and the hydration of an alkene, both those cases, you make a carbocation, water attacks it, and that gets you. That was chapter 8. Also in chapter 8, there's more to this reaction. I'm not going to deal with it right now, but you can look it up. When I teach this reagent in Orgo 1, I just teach it as osmium tetroxide. Pretty much all of your professors are going to have some differences in like what little minutia we think is important. I don't think all the other reagents here are important. Get Dr. King, she did. Anyway, this is syn addition of the two oxygens. You can also do anti-addition, a reagent called MCPBA. So this is one. This makes an epoxide, which we're going to talk about in chapter 13. So an epoxide is just an epoxide that's 3-membered ring with an oxygen. 3-membered rings have a lot of ring strain. So normally you can't break a CO bond unless that O is attached to a tosylate or something like that, right? Here you can because of the ring strain. And then this can go either through aqueous acid or alkaline, aqueous acid or aqueous base. And this will give you a transdiol. Right? Anti-addition of the two OHs. There's also the halohydrin from chapter 8. If I treat cyclohexane alkene with bromine and water, I'll get anti-addition. Get an alcohol. This is all review. All those that make a chiral product should get an enantiomer as well. Like you don't need to have those, you know, the last time you saw that was March 3rd, and that's fine. You don't have that to memorize at this point. But we review that a little bit. There's a couple of other reactions of that you might have seen that we'll talk about. I'm not going to go into the mechanism just yet. Or maybe at all. The mechanism would tell you why phenols don't do this. The carboxylic acids do. Carboxylic acids and alcohol will both do this reaction. Everything's still on the board. So if I treat an alcohol with SOCl2, thionyl chloride, I get an alkyl. I turn the OH into a chloride. It's basically the reverse of this SN2 reaction. You can't reverse the SN2 reaction, right? Directly. So at equilibrium, if I have propyl chloride and sodium hydroxide, equilibrium favors having the alcohol and the chloride. Right? You're basically trying to make the weaker base. Hydroxide is a way stronger base than chloride ion. So if I have the OH bond to the carbon and I make a chloride ion, I've made everything more stable. To go the other way, we have to go uphill first. So thionyl chloride has to react to the oxygen. That basically turns that oxygen into a leaving group that's good enough that chloride can boot it out. The mechanism is, I don't know if it's in chapter 12, it might be back in chapter 7 or 8 or something. I'm not going to ask you this mechanism right away. On the one hand, I'll let you know before the exam if I'm going to ask you this mechanism. I probably am not. There's a lot of new chemistry to get to. I'll hope that you have seen this. But just keep in mind like stabilities, okay? So if it looks like in one step it's unfavorable, then there's probably the reagent's probably doing other stuff, right? The reagent, oftentimes the job of the reagent is to destabilize the molecule you want to react enough that it does something else. The other thing on these two, there's nothing magic about chlorine on top or Br here. So you can have SOBr2 and you can have PCl3. PCl3 is pretty common. We use PCl3 a lot. I've never seen thionyl bromide. And most of that is just like what's made industrially. So if I need to turn an OH into a leaving group, if I have thionyl chloride in my lab, I use that. If I have PBr3 in my lab, I use that. I guess the other one that you would see would be posylase, so polyl chloride and base. And turn an OH into a leaving group with polyl chloride. That's also in chapter 7. You can protonate an OH, but you can't protonate an OH to make it a leaving group and have a strong base around, right? So again, basic fundamental principles. You can't have strong acids and strong bases in the same mixture. I don't know why I made that. Okay, so that's all stuff you know. Sorry to phrase it. It's all stuff you've seen. There is another way to make an alcohol, and that is to reduce a carbonyl. I'm going to draw all this up here and then talk. So, like I said, way back down at the beginning when you guys thought I was just joking around about drinking. If you drink ethanol, you've got an enzyme. It doesn't behave this way at all. But you have an enzyme that will convert ethanol to acetic acid. That is, you have an enzyme that will oxidize ethanol up to acetic acid. The reverse reaction of an oxidation is a reduction, right? So I can go from the carbonyl version down to the alcohol. So if I add H to a carbonyl, I end up with an alcohol. I basically have to add 2 hydrogens. And so the reaction you guys will have seen, and I know you've seen it because it's on the exam, right? You guys will have seen this reaction. This is a reduction. Put some stuff there. Right? If I treat an alkene, a carbon-carbon double bond, with hydrogen gas and some transition metal like palladium, I'll add the 2 H's to each carbon. Break the pi bond, I'll add each H to a carbon. So you can imagine doing that same thing to a carbonyl. Right? Looks like a very similar reaction. And you can't, that actually happens. Of these two reactions, the top, hydrogenation of the alkene is faster than hydrogenation of a carbonyl. Right? Carbonyl is a little more, there's two factors there. Carbonyl is a little more stable, and the carbonyl is more electrophilic, so it's more polar. All right, so if I have a molecule that's got an alkene in it and a carbonyl, and I like hit it with 1 atmosphere of hydrogen, room temperature for like an hour, I'll hydrogenate the alkene, and I won't touch anything else. If I hit that same molecule with like 100 atmospheres of hydrogen and heat it up to 100 degrees, let it go for a week, pretty much all the 5 bonds except the benzenes will get hydrogenated. Right, so you can always adjust that. So as we go forward, just keep in mind, hydrogenation conditions will sometimes reduce a carbonyl. If you need to, though, you've got to hit it a lot. All right, so what's going on in the next panel over? These are examples of polar reductions of carbonyls. And essentially the way this works, so think about so sodium borohydride, NaBH4, charge on the sodium is +1, means the BH4 has to be -1. Right, so BH4 polyatomic ion, kind of like ammonium. It's just that NH4 is positive. So if you look on the periodic table, right, NH4 is positive, CH4 is neutral, BH4 is anionic. In both of these cases, the formal charge, right, the formal negative is on the boron, formal positive is on the nitrogen. But because of the electronegativities, these H's are partial positive. And if you have a base react with NH4+, right, if I add like hydroxide to NH4+, the OH grabs an H, doesn't bond to the nitrogen. Same thing is going on over here. The electronegativities are such that the H's are partial minus. NH4+, you can think of NH4+ as a proton, though, right, as an H+. There's never really an H+ anywhere in solution, right? Protons are way too greedy for bonding. So you can make protons in like super colliders and stuff like that. Outer space, you can have protons. On Earth, in the atmosphere, any proton you have is quickly going to be bound up with something. Same thing is true with hydride. All right, you're never really going to have a naked H- atom floating around. But we have a lot of reagents that act like H-. So if you guys are used to NH4+ acting like H+, think about borohydride and then aluminum hydride as well as H-. It works out that borohydride is a weaker source of H- and aluminum hydride is strong. Okay, so the mechanism here, as far as I'm concerned, it's going to look like this, right? Polarity of that carbonyl is what you've seen before, right? That carbon is strongly partial plus, the oxygen is strongly partial negative. So this is like a really important mechanistic type we're going to see. Basically, most of the mechanisms we're going to see over the next few weeks, you've got some nucleophile adding to the positive end of a carbonyl. All right, carbon can only have 4 bonds. So if a nucleophile adds that, there's got to be a leaving group, right? Nucleophiles that attack carbons have to kick out a leaving group. Here, the leaving group doesn't leave. The leaving group is the pi electrons that pop up onto the oxygen. And now think about stabilities. O- is a lot more stable than H-. And like I said, I just want to come back and emphasize, this is a lot more complicated than I'm letting on. Like neither one of these reagents is an H minus. And what ends up happening is this O minus ends up bonded either to the boron or the aluminum. Oxygen makes a really strong bond to boron and aluminum. And that's what drives this reaction. Or it's a lot of what drives this reaction. And now the second step, I hope, is obvious. You need an acid source. So some acid here to protonate the O minus. Right? If you run the reaction in methanol, that proton source is just methanol, right? The OH on the methanol. So basically, sodium borohydride is a weak enough reagent. It's a weak enough base, a weak enough nucleophile that it can swim around in methanol and not react. Lithium aluminum hydride, you see I've got these numbers here, right? A 1 and a 2. Lithium aluminum hydride is a strong enough nucleophile and base that if you put that in methanol or water or ethanol, it's going to react with the solvent. So another really common thread of what we're talking about the next few weeks, what the solvent can be. A lot of times, like that Grignard you guys did in lab, the solvent has to be dry. And when I say dry, I don't just mean water. I mean, it can't have OH groups. So like that Grignard can't have water. It also can't have methanol or ethanol or acetic acid or phenol or anything like that, right? It's got to have solvents that are not protein. Right. So this is going to be the mechanism for reduction of carbonyls. We're also going to see oxidation reactions. I'm not going to put those up just now. I'm going to talk about oxidation. Are there any questions about what I've done so far? Getting to the point where even my funny stories about beach funerals don't keep you engaged. So I think I'll finish with this, and that's going to be enough of an introduction. You guys have had a long week. It's always fun to hear you've had a long week on Wednesday. Jerk. All right. So I am going to ask you in here. I'm going to ask you, is that an oxidation or is that a reduction? You can never have, it's like an acid-base reaction. You can never just have something oxidized. You can't have something reduced. If something gets oxidized, something else has to get reduced. Something gets reduced, something else has to get oxidized. But I'm an organic chemist, so what I care about is the organic, right? So I would say over here, this is a reduction reaction. I didn't even draw the boron, right? What happens to the boron? Well, boron is like a big part of this reaction. Boron gets oxidized to boric acid, BOH, BOH3. All right, so the boron gets oxidized, the carbon gets reduced. I'm an organic chemist, I only care about the carbon. It's an inherently unequal, discriminatory point of view. But these guys don't have to. So this is a reduction because the organic thing gets reduced. Going the other way, right? If I took isopropanol and oxidized it to acetone, that would be oxidation. Even though there's got to be a reagent in there that gets reduced in the process. So we need to think about how to calculate oxidation numbers. So remember that in formal charge, the rules for formal charge is this. Split all shared electrons equally. I got an oxygen and a hydrogen bonded together. I say the H gets an electron, the O gets an electron. Oxidation number, we don't do it that way. This is really, if you can calculate formal charge, you can calculate oxidation number with just a little bit of practice. The only change you make is when if two atoms share electrons, give all of those electrons to the more electronegative atom. You guys already do this pretty naturally, right? Over here, nobody blinked when I drew these particle charges with carbonyl. Plus oxygen's partial minus. You look at it and you're like, that oxygen's taking the electron. In oxidation number, we just do that to an extreme. So let's calculate these. I'm going to go through this. 10 minutes left in class. I'm not going to make you try to follow. First thing is kind of go in and put all the atoms on here. Something else in general, bonded to carbon. Sorry. Right, in a CO bond, the oxygen's going to get two electrons, carbon's going to get none. In a CH bond, the carbon gets two electrons, CH gets none. All right, so here, I'm going to redraw this molecule. The carbon-carbon bond is going to split evenly. Carbon and carbon, they're the same electronegativity. We're not going to pay attention to like inductive effects and would there be a little bit of a polarity there or anything. We're just going to say carbon gets one electron, the other carbon gets one electron. So I'm going to write C on the carbon I'm calculating. So I'm calculating the oxidation number of this one. CH, carbon gets 2, H gets none. CH, the carbon gets 2, H gets none. CO, the oxygen gets 2, the C gets none. Is that okay? All right. How many valence electrons should carbon have? No. How many bonds is carbon? 4 valence electrons. That's what we're going for. So the oxidation number is 4 valence electrons minus 5 actual or calculated. So that's minus 1. So the oxidation number of the carbon bonded to OH and propanol, 1 propanol, is minus 1. Okay, take 2 minutes and try to do the oxidation number for propanol. The middle. Take my mask off. The big smile. Okay, so again, we're looking at this carbon bond, split the 2 electrons equally. Carbon and carbon have the same electronegativity. Carbon and oxygen now share 4 electrons. All four of those go to oxygen. H gets none, so the carbon gets 3, or it gets 2. So the CH electrons go to C, the OC electrons go to O, the CC gets split. So the oxidation number here is 4 valence electrons minus 3, that's equal to plus 1. All right, again, this isn't a charge, it's an oxidation number, just like formal charge, it's bookkeeping. But it does let you tell whether the atom in question has been oxidized or not. So minus, let me say this more generally. All right, so if the oxidation number becomes more positive, that atom has been oxidized. If it becomes more negative, it's been reduced. What if it stays the same? Not an oxidation. Not an oxidation or a reduction. So if you look at the reactions on the board, I cleverly erased the one I was going to use as an example. This lets you sort of there's a quicker way to do this. So there's this SN2 reaction. So has this carbon been oxidized or reduced? What's that? Neither. You don't have to do math. I realize I'm complaining about doing arithmetic with numbers smaller than 5. But you don't have to do that. That carbon is bonded to a carbon, 2 hydrogens, and a heteroatom, an atom more electronegative than itself. Over here, it's bonded to a carbon, 2 hydrogens, and an atom more electronegative than itself. That's going to be the same oxidation state. I don't have to know what the oxidation state is, but it's the same. How about this one? Neither again. 2 bonds to carbon, 2 bonds to something more electronegative. 2 bonds to carbon, 2 bonds to something more electronegative. The center carbon has been reduced. So this carbon right here. How do I know that? Well, I've got 2 bonds to carbon, 2 bonds to more electronegative atoms. Over here, I've got 2 bonds to carbon, 1 bond to an electronegative atom, but one of my bonds to an electronegative atom has been replaced with a bond to H. I didn't draw the H, that's being tricky. Right? If I replace a heteroatom, if I replace a more electronegative atom with a less electronegative, like an atom either the same as carbon or less, that would be a reduction. Right? If H replaces a more electronegative atom, the electronegative atom is going to take the 2 electrons, the H is going to give the 2 electrons. Okay, so a way to sort of, again, sort of, if you want to generalize, in an organic molecule, right? So if I'm looking at a carbon and I have a hydrogen replace a more electronegative atom for a carbon, that's going to be a reduction. If I have a more electronegative atom replace a carbon or a hydrogen, that's going to be an oxidation. Or actually, a carbon replacing a hydrogen is also an oxidation. We don't usually think about it that way, but making carbon-carbon bonds is a little tricky. It's an entirely different topic. You can't follow oxidation numbers. So again, that's a lot. If you didn't, and I have a strong suspicion that after the exam on Monday, nobody rushed home to do a bunch of homework in chapter 12. I don't know how I know that. Actually, ethanol is in chapter 12, so maybe you did. Anyway, next class is Monday. So before Monday, read through chapter 12. I'm going to assign a few problems just because it's 5 days. They probably won't get up till this evening or tomorrow either. And then, like I said, what you should expect to see from me is an email that's got a PDF of your exam. All right. So you don't have to come pick my exam up. You don't have to come pick the exam up from me. And then I'm going to have some time available, hopefully Thursday afternoon and on Friday, that you can come talk to me if you want. You can come talk to me on Monday. I'll sit out here after class. I do not want to encourage anyone to drop who really doesn't want to. But I also don't, I want you to get an honest assessment of where you're at, right? If you made a 35 on this test, like there's both the fact that you've got to catch up with that material, maybe you got to catch up with 122 material, and you got to make up a bunch of points, right? The mathematics are bad for you at that point. Also, if you made 100, I don't know if anybody did, but if you made 100, congratulations. Like I said, that's 20% of your grade. If you don't get any more points in this class, you make an F. So, you know, like I said in that long email, if you made a 95 or something, congratulations, you're doing fine. Like, don't change anything, but also don't stop. So, all right. Those of you in lab, I'll see you in lab. Those of you not, I'll see you later. You're welcome. See you all.